So before lunch, I think we have time till 12:30 because the room might be reserved. So the schedule. I guess 1 hour will be fine. So recent talk will be treated for us to read
So thanks for being so flexible to accommodate this change in schedule. This talk will be about GPDs and transverse geometry in high energy PP collisions. And I'd like to put this in the context of current events in Washington. You hear a lot these days about respectable people who have apparently a secret life that you could hardly imagine. And the same is true of GPDs. As I'm going to show you, they're very respectable. They appear in the context of electron scattering, we have factorization theorems, etc. But they also have a secret life in proton-photon collisions, which are much more, let's say, dirty, lots more things going on. As I said, this is actually a very interesting subject. Or more seriously, what I want to tell you about is that if you know the transverse spatial distribution of partons in the nucleon from electron scattering from GPDs, then we can understand many aspects of proton-proton collisions with hard processes. Specifically, we can control the transverse geometry in PP collisions with hard processes, or understand the dependence of the cross-section on the impact parameter. In this way, we can understand quite a few features of these collisions. For example, how the underlying event depends on having a hard process, things like hard-soft correlations. We can understand the probability for multipart interactions, and we can also compute things like the gap survival probability in sample exclusive diffraction, etc., etc. So that's a whole complex of interesting topics, and I've been working on that on and off with Lonja Frankfurt and Mark Strickman for almost 15 years now. As I said, there's really two directions in here. So what I will mainly show you is that knowing the GPDs from electron, proton, gamma proton scattering, we obtain very valuable input for the analysis of high energy PP collisions that will help us to understand features like the underlying event, multipart interactions, etc. But we eventually can hope to reverse this direction and actually use high energy PP collisions as an additional source of information on the GPDs. So here's the outline. We will start with a brief review of hard processes in PP collisions, the standard factorization for the inclusive cross-section, and we'll see what other observables are there pertaining to the underlying event and how they are correlated with the hard process. We will then briefly review the transverse distribution of partons, which is encoded in the GPDs that are measured in exclusive processes in BP and gamma P. And I can be very short about this part because this should be well known to everyone in this audience. And then we will look at applications of GPDs to the transverse geometry in PP collisions. We will see how we can understand hard-soft correlations, calculate the probability for multipart interactions, and then we will look at a particular hard process, which is central exclusive diffraction in PP, where we will see that we can understand the physics of what's called rapidity gap survival in this geometric picture. So let's start with hard processes in PP. So we all know that for the inclusive cross-section of a hard process, we can separate the transverse momenta at the hard scale, m squared, m is the mass of the produced system, which is much larger than the hadronic scale. So we can separate the transverse moment at that scale from those at a soft scale and obtain a standard factorization in which the inclusive cross-section is expressed as the product of the parton densities in the colliding protons times the cross-section of the hard process. These parton densities are the one-body densities of partons in the colliding protons, and they are actually the same as in electron-proton deep inelastic scattering. So this is all well known, but I would like to emphasize this is true for the inclusive cross-section where we sum over all final states and do not put any additional restrictions on it or ask any additional questions. Now in practice there are many other observables that one can study in PP collisions event by event. These are called the underlying event characteristics. Those can be the number distribution of particles, of hadrons produced differentially in rapidity and transverse momentum, the different species. It can be things like the average transverse momentum or energy flow variables. So there's a whole host of such observables. And they, as I said, they refer to what is called the underlying event, so the other interactions accompanying this hard process. And these are mostly soft interactions that are not associated with this hard scale. Although we will see that in some cases, particularly in high energy collisions at the LHC, there can also be events with multiple hard processes, and it's actually a very interesting topic, how to define and how to isolate such multiple hard interactions. So there are many underlying event characteristics, and a very interesting question is how are they correlated with the hard process? So how does the underlying event depend on this hard process and its variables? For example, a very basic question, is the underlying event, all this, say, multi-hadron production, is it different in events where we have a hard process as compared to what's called minimum bias events, where we just trigger on having some inelastic interaction, but not necessarily a hard process? Very basic question. Or more quantitatively, how do the characteristics of this underlying event change with the kinematic variables of the hard process, with the basically the rapidity and the mass of the produced system? This is a very interesting question for several reasons. One reason is that it allows us to understand strong interaction dynamics in these proton-proton collisions at high energies. Another reason is it can facilitate the search for rare hard processes by enabling cuts, experimental cuts. So imagine you're looking for new particle production, some extremely rare hard process, and imagine you knew that the underlying event in such hard processes had certain characteristics, then you could cut your event sample down to those that have those underlying event characteristics and look for your exotic hard process in that sample rather than in the whole sample. So there's a very practical interest in understanding the underlying event in hard processes. And of course, if we go to that level of question, we have no strict factorization anymore. So additional assumptions are needed, but that shouldn't say prevent us from going there. And here I will present an approach that is essentially based on the transverse geometry of the collision. It provides limited information, but it's model independent, and I would contend that it's very useful overall. And clearly, if you ask more detailed question, this would be something you have to implement and study at the level of a Monte Carlo generator. but as I show you, certain aspects of these hard-soft correlations and the underlying event characteristics can be understood on the grounds of the transverse geometry alone. Let's talk about how we can understand this, say, this underlying event, or this, say, a soft particle production more intuitively. And that comes back to something we say, encountered several times earlier this week, namely a kind of wave function picture of the partonic structure of the nucleon. So intuitively, we can understand this as follows. We can think the nucleon as being described by a partonic wave function, which is really a superposition of configurations with different particle number and different spatial size, etc. It's a very complex, almost like a mythical object, and no one in his right mind will actually try to write it down or do calculations with it. But it's very useful to keep in the back of your head as a kind of basic underlined object. And then the parton densities that we see in the inclusive cross-section, they are just the one-body density is derived from this wave function, so they are the sum of the amplitude square, the component square, in which we have a parton with a given x, but otherwise we sum over all configurations. And now, and in the inclusive cross-section, that's all we need. But in the underlying event, we're actually seeing interactions of these spectators in the wave function. So it's
Christian,
yeah.
Before you move on to Korean recap, you're working in certain games, right?
Generally, this question is way too advanced.
Yeah. Frame, even though the result could be frame independent.
Yes, yes. As I said, I'm not proposing this as a way to actually do calculations, but as a kind of intuitive picture.
That's exactly the definition of PDF. PDF
is to guide what kind of. So I will actually, I will not. I want you to keep this in the back of your head. We will not use any detailed information about this wave function. We will do some very limited studies just based on the transverse side, the average transverse size of the configurations.
So it is usually light gauge.
Yeah.
It is usually light gauge. There is no other way. Light gauge.
Yeah, that's why I said it's a gauge kind of process.
Yeah,
it's gauge
is always only
yeah.
defined in this gauge.
That's right. Otherwise,
There's no other way to get away.
There's no other way.
Yeah. So before we go on, we have to briefly talk about the kinematics of the hard processes we're going to study. And generally, the momentum fractions x1 and x2 of the active partons are given by the ratio of m squared over s, where s is the proton center of mass energy. For example, if you have a back-to-back dijet pair, a dijet at zero rapidity, this m squared would be given by 4 times the transverse momentum square. If you're talking about Higgs boson production, this would be really the square of the Higgs boson mass. And I just like to say that the typical x values that we're encountering in these hard processes at the LHC are in the range between 10 to the minus 1 and 10 to the minus 3. So they're not extremely small. They're also not extremely large. They're exactly in the region where we measure PDFs, GPDs with HERA, COMPASS, and the electron ion collider. And just as an example, these are this is the kinematic coverage in, say, x1 and x2. These lines here in the xq² plane for 2 sets of hard processes at the LHC. This would be dijet production with a PT of 2 GeV and a rapidity below 5 and PT of 10 GeV. And you see we're exactly in this region between 10 to the minus 1 and 10 to the minus 3, where we have some information on the partonic structure from and the GPDs from existing experiments, and where we hope to measure them with the electron-ion collider. So let's talk about the transverse distribution of partons. And as I said, about this part we can be very brief because it's well known to everyone here. We know we have a factorization theorem for hard exclusive processes such as exclusive meson production. It's based on the idea that this system is produced in a small size QP bar configuration. And then after factorization, all the information about the nucleon is that enters is contained in the GPD, which is something like the partonic form factor of the nucleon. It's universal, it's process independent. It has an operator definition as a twist-2 matrix element, etc., etc. And as we know from the work of Matthias and others, if we take the Fourier dimension, the two-dimensional Fourier transform of this GPD at this is now in the diagonal case, x prime equals to x. And then we obtain a function of some two-dimensional coordinate variable, which we call rho here. I should say I will reserve B for the proton-proton impact parameter later on. We obtain this function f of x and rho, which describes the transverse spatial distribution of partons in the nucleon with a given x. And it amounts to a kind of tomographic image of the nucleon at fixed x, which however changes with x and q squared. So there's a lot of interesting, not just structure, but also dynamics in these distributions. And we heard a lot earlier this week that at large x, where we show most of the quark GPDs, there are polarization effects, we deal with large skewness, and the JLab 12GE program is mostly about that. And so for the applications that follow, we'll be mostly interested in the transverse spatial distribution of gluons. And here we actually have quite good information from the HERA experiments, and it's worth summarizing that briefly. So we have data on exclusive J-psi production at HERA, also phi and rho electroproduction at large Q square, which all probe the gluon GPD in this logic. At large X, there's some data from a Fermilab broadband photon beam experiment from COMPASS. There will be JLab 12 phi, exclusive phi data. So one can extract the transverse profile of the gluons just from the relative T dependence of the exclusive cross section. We don't need the absolute cross section. So a lot of the theoretical uncertainties associated with, say, finite size of the vector meson, etc. They go mostly into the absolute value of the amplitude, but they cancel out in the ratio.
But that depends on Q squared.
It depends on Q squared. I get to that in a second. And we can get the gluonic transverse radius of the nucleon directly from the T slope of J-psi production. So if the T dependence is described by exponential, the average rho square of the gluons is just twice the exclusive, the B slope of the exclusive.
So there must be some assumptions behind that statement, right? You have the psi gluon distribution in the psi, you have the gluon distribution in the proton.
No, the psi is the pro.
But it has its own gluon distribution. How do you?
So according to this logic, the psi is the J-psi is a probe. It's like this. It's like a CC bar dipole that pokes through the nucleon at a given impact parameter, and by the logic of factorization, we assume that this the transverse size of this CC bar dipole is much smaller than the hadronic size. Then the hadronic, but that's inherent in factorization already. So the one
down T, because Q square has to be much larger than T for your formula to start to be valid.
Wait a second. The real thing is
T has to be much smaller than Q. Yeah, otherwise,
I agree. Your delta perp, your transverse momentum transfer to the neutron, should be much smaller than the inverse size of the CC bar diagonal. Actually, but that, as I said, that's all contained in the logic of factorization. And in extracting this transverse distribution, we've actually made a small finite size correction for the J psi, which is purely empirical. It goes beyond strict leading twist, but it's it can be justified. I don't want to go into that level of detail here. So this figure summarizes what we know about the average gluonic radius of the nucleon as a function of x from these said experiments. There are yes.
Also ask them. I mean, yesterday we had a lot of discussion about how complicated it is to describe shape psi production.
Yes.
So this here says that if we are just interested in that quantity, all this discussion is basically irrelevant.
No, this is saying that on the basis of the approaches that we have, which is, say, leading order plus finite size corrections, and which is here in particular the one by Frankfurt Strickmann curve, which is tested against many observables. It describes the absolute cross sections of J psi production. It describes the energy dependence. It describes the Q-square dependence, and it is based on some effective scale setting in the leading order formula. So I don't want to relitigate all these issues, but on the basis of that approach, we can extract that this gluonic size of the nucleon. And I'm quite confident that most of the corrections we discussed would affect the total cross-section, but would have a relatively minor impact on the relative T dependence, which is what
very good.
which is what we're interested in.
I mean, not news, but it's very
So there's several interesting observations here. The first is that the gluonic radius, average rho square of the nucleon, is actually much smaller than the soft nucleon radius, which you would say is of the order of 1 Fermi square. Here you see that this is like between 0.2 and 0.4 Fermi square, and we'll make this more quantitative in a second. And yeah, just
isn't this log for J psi something around 5 and
it's between 4 and 5. Between
so 5 times 2 observed. So how we get the units?
5 by 25.
But
yeah, it's from inverse GB to Fermi as a factor. Yeah, it's 5 Fermi squared is 25. So the second interesting observation is that this transverse gluonic size of the nucleon grows as we go as we look at smaller and smaller x, and it grows with an effective Regge slope, which you call alpha prime gluon, which is about 0.14 inverse Jeff square, which is noticeably smaller than the slope of the Pomeroy trajectory, the growth of the size of the nucleon in soft interactions. That one would be about 0.25 inverse Jeff square.
This is 0.14 is a fit parameter.
It's a fit parameter. Yeah. Yes, I mean, it's yeah. So, and that, if you like, notions of Gribov diffusion shows that Gribov diffusion as a model for the soft Pomeroy slope, it would show that it means that Gribov diffusion is suppressed in the distribution of partons with a significant KT, and that again that can be easily understood on grounds of the effective momenta in the partonic ladder. But that's a separate subject. So this transverse distribution of gluons also changes as a result of deglap evolution. and one can easily understand that the evolution, D-glab evolution implies that the partons basically decay locally in transverse space, at least on the scale of their variation inside on the scale of the spatial variation inside the nucleon. And then the effective size changes with Q squared, because as we go up and up in Q squared at a fixed X, we're seeing, in some sense, images of the image of the mother partons, or the input of the D-glab evolution, which sits at larger X, where the transverse size is smaller. So that's a very interesting effect. The effective size changes due to D-glab evolution, but it's a very small effect at Q squared once we are above a few GV squared. So this will be largely irrelevant for what follows.
Where does this come from? I mean, in your mathematical way.
If you like,
I mean, D-glab evolution doesn't really involve T.
D-glab evolution doesn't involve T, but it changes the X dependence. So if you like, you have a model of the diagonal GPD at some scale. So you have a correlated X and T dependence at some scale.
Okay.
You apply D-glab, and then it means at a fixed T you will have a different X dependence. So it's not.
Would you expect to see saturation in this quantity as you go to smaller X? I mean,
saturation is a loaded word.
No, I mean, basically the object. All what I'm saying is the object cannot keep growing, and if one is brave, if you go to very small X, maybe one could see perhaps. I think
you should discuss this with John, where he has notions about confinement in the distribution of small partons at small X. For what I'm going to present here, this is this question does not arise because I'm interested in partons at relatively moderate X, and it's a very interesting question. I mean, it concerns things like the Froissart bound in high energy scattering and how it's realized in QCD, and so let's have this discussion elsewhere. So let me come to the main point now, which is I want to show you how we can use this knowledge in understanding the transverse geometry in proton-proton collisions with a hard process. So such a hard process is induced by a binary parton-parton collision, and the scale of the partons, the typical KT of the partons, they are of the order of the scale of the hard process. So on the point is that we can think of this hard process as basically local in transverse space, at least local on the scale of the variation of the distribution of partons in the colliding nucleons. And then one can actually think of this proton-proton collision for a moment as happening at a given impact parameter. Of course, the impact parameter is not an observable variable, and one has to integrate over impact parameters eventually. But for a second, we can think of this collision happening at a fixed impact parameter, and then we can think of it as like differentially in impact parameter, and then we can calculate the probability for having an overlap between two partons with given x1 and given x2 in a given point of space, given a certain proton-proton impact parameter. So this is just this basically geometric overlap of the transverse distribution of gluons in the two colliding protons with a displacement that is given by the proton-proton impact parameter.
So you're assuming that the partons are gluons.
Eventually, I'll evaluate this for gluons. So, I mean, the concept as such is general. You could use it for any kind of parton-parton collision. So, but the point is that this quantity is a theoretical quantity. It's calculable from the known transverse distributions of partons in the colliding protons. And the integral of this of this quantity over B just reproduces the standard inclusive formula. And then this convolution integral collapses and we just obtain the usual product of the integrated gluon distributions.
How do you calculate this without
I don't need it here. It's basically a local quantity. It's just here so that I can call this the cross section. And then when I integrate over B, I obtain the usual.
But it should depend on the row 1, row 2.
No. No. The hard process is local in X, and it doesn't care about the position. It's local in transverse position.
But there's on your right-hand side, your G should have a scale dependence on the Q.
Yeah.
Large scale dependence Q.
Yeah.
That G was extracted from the process from at the scale Q.
Yeah.
So that would be relevant.
Yeah.
Absolutely.
I just didn't write the scale dependence here. So as I said, this is really it's a theoretical quantity. It's a generalization of the inclusive factorization formula, and collapses to the latter in case that we integrate over B. And it defines, as I said, the probability to have this binary parton overlap as a function of the PP impact parameter, or conversely, it determines the effective impact parameter distribution in proton-proton events where we have such a hard process. And it's convenient to define a normalized distribution where we divide this by the integral. Then we obtain a distribution that is really such that its integral over d2b is 1. And we can think of it as describing the normalized impact parameter distribution in PP events where we have a hard process.
So where are repeated divergences hidden in such a form?
Oh.
So it's not a question of just independence. We know that the additional squared is one thing, but there are also other divergences. The repeated divergences there. That means that
there's no transverse momentum dependence. This is in the context of collinear factorization. All I'm using is that on the scale of, as I said, the proton size, the hard process happens basically locally in transverse space.
But I think that it is simply it is not collinear factorization. It's actually TMT factorization in a sense, but sort of leading order. No, the difference that you write it in impact parameter space is not an issue. You can write it in different relation in parameter. Yeah, it's not an issue, but this is.
By the way, it's a very interesting question how this could be derived, and then this in a TMD-like setting where you have, in some sense,
I would say that your G's are up to definitions for your transform.
Yeah, I think it's important to let Christian say the main idea of this talk, which I don't think he's reached yet. And you're getting towards the deadline.
So, as I said, this is a theoretical quantity. It describes the impact parameter distribution in PP events where we have a hard process. And it's really new information. And on the basis of that new information, we can calculate or understand several interesting things. So we can model the spectator interactions now, depending on the impact parameter. and see how they are, and in this way understand how they are correlated with the hard process. You can predict the probability of multiple hard processes or multi-part interactions, and we can understand the issue of probability gap survival in diffraction. So before we do that, we want to compare the impact parameter distribution in PP events with a hard process with the impact parameter distribution in so-called minimum bias events, where we just have some inelastic production, but no other, not necessarily high transverse momentum. So how can we get that? Well, we can get that by using the proton-proton elastic scattering amplitude, which through unitarity contains information also about the total and therefore about the inelastic cross-section. And here we use a well-known technique where the elastic, so this is the proton-proton elastic amplitude, it's a function of S and T, and it's represented here in the so-called impact parameter representation, where as in the case of GPDs, one assumes that the momentum transfer T is in a transverse direction, and then there's a two-dimensional Fourier transform. And this function gamma, which is known as the profile function, it's something like the proton-proton amplitude in impact parameter representation, and one pulls out a kinematic factor here, including a factor I, and that gives this gamma a particular kind of interpretation as some kind of say grayness or blackness of the target. For example, one could show that the scattering from a black disk would correspond to gamma equals 1 inside some radius. And there's lots of interesting intuition and phenomenology around this gamma. And as I said, it's just a representation of the PP elastic amplitude. And this is actually the way in which the data on proton-proton elastic scattering and total cross sections are analyzed. And our organizer, Alexei, has participated in this activity. And now, having this gamma profile function, we can now represent the elastic and the total PP cross section as integrals over impact parameter. So the elastic cross section is given by the modulus square of the scattering amplitude, and that turns into basically the modulus square of gamma. The total cross section by unitarity is related to the imaginary part of the PP scattering amplitude, and that in the gamma representation turns into twice the real part of gamma. And if we take the difference of the two, we obtain the inelastic cross section, which after some rearrangement can be written as the integral over d2b as 1 minus gamma squared. And notice that all these are integrals over b. So the integrands here give us respectively the probability, the distribution of the elastic, total, and the inelastic cross-section over PP impact parameters. And again, we can define some normalized B distributions where the information on the total cross-sections is factored out. And we are particularly interested in the B distribution of the inelastic cross-section, because that gives us the effective impact parameter distribution in minimum bias PP events. And so we can take some parameterization of the PP elastic amplitude at the, say, LHC energies and evaluate this function. And it's shown here in the blue line. And you see, so the black lines here are the impact parameter distributions in hard PP events with the hard process here that we derived earlier from the GPDs. You see that the impact parameter distribution in these minimum bias events is much broader than the one in in events where we have a hard process. There's really almost a qualitative difference between the effective impact parameters in PP collisions with a hard process and in minimum bias collisions. That will be very important for what.
And as Jean-Louis said, actually, one of the reasons for that is that you have hard scale in one, and then in this soft scattering, you don't have this hard scale. You cannot compare them directly because those
not so much the hard scale. It's more like that you force the geometric overlap at a given point in space.
Correct.
And then the fact that the spatial distribution of the hard partons, of the large X partons in the proton is much smaller than the apparent size of the proton in soft interactions. There's actually, I'll get to that exactly on the next slide. So these findings from the plot we've just seen mean that the transverse proton size in soft interactions is much larger than that in hard processes, the apparent transverse size of the proton. So if you like, you can express this in terms of some range of interaction or effective size of the proton as it participates in these interactions. We can say that the effective radius of the proton in soft interactions is much larger than the average row square of partons with a significant x, say x larger than 10 to the minus 4. And I'll show you values for these quantities later on. They're really very separate, so we're really dealing with two scales in the transverse proton structure and in high energy collisions. The area occupied by partons with some significant x, and the area of the proton as participating in soft interaction.
Isn't it trivial from the point of view of GPDs? You have the partons with larger x, which should be closer to the center of mass.
It's not well. You would not describe soft interactions by GPDs. For that, you need something like Rebov's parton picture, which is really, a new concept. So GPDs tell us about this size of large X partons, but not about the size of soft interactions.
So soft interactions which have smaller X, they can be far away from the center of mass. So that's basically the punchline, right?
It's not unnatural, but you don't get this from GPDs. This is really soft physics. These are, if you like, V partons in Rebov or Feynman's language. It's not the stuff that goes into the factorization theorems.
Right. But those pictures, but you have small X very localized. Large X very localized and small X very diffuse.
I'm saying it's not in contradiction with GPDs, but I'm using it. I'm using the GPDs for this information, and I'm getting that size from completely empirical information. I'm not saying that soft interactions are initiated by partons or anything. I'm getting just a nondescript proton size in soft interactions. The important thing is that we really have two very different scales in area, and as such we have two classes of proton-proton collisions. Now we have what we call peripheral collisions, in which only these larger disks overlap, and these account for most of the inelastic cross section. And we have what we call central collisions. Those are the ones in which these smaller disks overlap, and in those we have a high probability for a hard process. Or conversely, if you select events in which you have a hard process, they are much more central than minimum bias events. And that has all kinds of consequences. But first, let me show you this plot here. So this is really the now quantitative statement. This is the median impact parameter. Now in PP events with a hard process, say with a jet trigger here. as compared to minimum bias events. And you see that just in the linear impact parameter, there's a factor of 2 difference, and the relevant quantity is really the area, the impact parameter square. So there's a factor 4 difference in these.
So is it just a statement that the jet cross-section, if you start with reasonable jets, is factor 4 smaller than the total inelastic cross-section?
No. It's a statement about the range of interaction in transverse space. That the total cross-sections are factored out. And these are defined as normalized E distributions. It's a statement about how a given cross-section is distributed over impact parameters.
Okay, then first the question: what is experimental refraction of jet events in the total inelastic cross-section of fluids?
It absolutely depends.
I thought it was rising within.
Yeah, it absolutely depends on the kinematic. And we will get to that on the next slide with multipart interactions. So
you might take the language of Hadian colleagues, because if you think of the proton as some kind of sphere, then in the middle, the probability to find the same impact on it doesn't have more partons more than the one in the surface. So if you take the language of Hadian things, then you could say that way.
Yeah. Okay, fine. If you have that kind of intuition, you can attach it to that. But so we have these 2 scale pictures, which is really based on just numbers we get from data. So let me show you what we can do with that. And as one thing we immediately see is that because collisions with a hard process are much more central than minimum bias collisions, we expect that the underlying event is very different. And in particular, this gives rise to some geometric correlations. So namely, if we have a hard process, we necessarily select central events in which then the event characteristics are different from minimum bias events. Let me show you that this is actually seen in the data. So this these are CMS measurements of what is called the transverse multiplicity. This is the multiplicity of particles produced in the direction transverse to a jet trigger, where we're not affected by the activity inside the jet direction, as a function of the PT of the jet. And you see that it's done for various energies, it rises and then becomes flat. And this can be understood absolutely naturally in our picture. This PT is really the PT of the jet trigger now. So if we trigger on a PT with a small PT, say a few GeV, those are basically minimum bias collisions. Those are very peripheral events. And as we increase the PT of the trigger, by our logic, we select more and more central collisions, where naturally the transverse multiplicity is much higher. But then from a certain PT on, if we increase the PT further, it doesn't change anything anymore, because once we have a hard process, the event is central, and it doesn't matter if you increase the hardness of the process anymore. It's already centered, and lo and behold, this is exactly what we see in the data. And we actually predicted this kind of behavior in our paper in 2011. And I'd like to say that this is something that is very difficult to reproduce in a Monte Carlo. You absolutely naturally get this picture if you have the impact parameter as a variable and implement this concept of selection of impact parameters by the hard process. If you don't have an impact parameter, just work in momentum space, it's very difficult to implement this in a Monte Carlo.
But it seems that they all agree with Monte Carlo.
Yeah. I mean,
So it was
they
difficult
learned
to
how to
manage.
do it, but it requires really massive tuning and very unnatural parameters. If you have your underlying geometry, you can get this for free. So in the last minute, I want to show you some further applications of this picture, namely to what's called multi-part interactions. In high energy PP collisions at the LHC, there's actually a significant probability of what is called of double parton scattering. That means two hard processes induced by two binary parton-parton collisions in the same PP event. This double part process rate is traditionally parameterized by a quantity that is called sigma effective, or 1 over sigma effective, which is defined as the ratio of the double dijet cross-section to the products of single dijet cross-sections with the corresponding longitudinal or inclusive parton integrated parton densities factored out. It's a bit of an unfortunate choice of this quantity, but it's not very intuitive, but it is what it is. So everyone uses a sigma effective. And the point I'm making here is that knowing the transverse distribution of partons in the colliding protons and making a mean field approximation where one assumes that the spatial distributions of these partons in the protons are not correlated, one can obtain a kind of baseline estimate for this multi-parton rate just on grounds of geometry. And the expression, I don't want to walk you through the derivation here, is given by this. Basically, it's the product of our overlap of our original B distributions for a single hard process, now multiplied and integrated over B, and this gives you 1 over sigma effective in mean field approximation. As I said, this is not the whole story, but it's a kind of baseline or reference prediction. And with putting in our knowledge of the transverse spatial distribution of gluons, we get a sigma effective of around 34 millibar. Now, why is this interesting? It's interesting because the actual data on double dijet production from CDF and now coming out of the LHC experiments show a rate that is twice larger than this geometric mean field baseline prediction, which is quite large, and it means that there are likely correlations between the partons that make this rate.
Well, we know that there's, first of all, there's what we call center of mass correlation. The momenta of the partons in the wave function have to add up to the proton, and you have effects of the Pauli principle.
That's not an issue because the X's that we're talking about are not that large. So you can, it's not like you take 30 or 40% of the light from momentum out of the loop. So this kind of recentering is a minor issue. We're really talking about more like dynamical correlations. But the point that I wanted to register here is that really the transverse geometry provides us with a baseline prediction of the baseline expectation for the rate, and then everything beyond that can be attributed to correlations. This is actually a very active subject, parton correlations in the nucleon. Maybe asking the question how the probability to find a parton is influenced by having another parton nearby. It's really a fundamental property of many body systems. It's going to condensed matter physics to nuclei. And Jeremy discussed something similar earlier this week. People have introduced so-called multi-parton distributions, which are the expectation value of now the product of two twist 2 operators at a certain transverse displacement RT in the nucleon. This is also a kind of GPD object. It's very interesting. I mean, this is not localized with respect to the center of the nucleon. It's integrated over all center of mass positions, but it's localized in the sense that we're specifying the transverse separation of the two lightweight, the two twist 2 operators. And there are many subtleties in the theory of these multiparton interactions. There are ultraviolet divergences, the renormalization of these multiparton operators, the mixing with one-body operators. Usually you can reach the same final state not just from a double binary parton-parton collision, but also from a single binary parton collision with some hard splitting. So, and it's a major challenge how to disentangle them. And but such parton correlations can be induced by perturbative or non-perturbative dynamics. Actually, D-club evolution naturally induces some positive correlation between partons, because we know that the active parton arises from the perturbative splitting, and that it has a partner nearby in a range RT that is given by the inverse normalization scale. There are also non-perturbative parton correlations arising from chiral symmetry breaking. For example, Peter Schweitzer, Mark Strickland, and myself, we discussed the effect of non-perturbative quark, anti-quark pairs in the nucleon that are associated with, in some sense, the chiral condensate or chiral symmetry breaking in the QCD vacuum. And all these correlations can affect the multiparton interaction rate, and it's a very active field of research. The conclusion for the moment is that perturbative correlations of this kind can explain the observed enhancement of the MDI rate beyond the mean field approximation. So, in the last minute, I would like to show you an exclusive process in proton-proton scattering, which is really almost the closest analog to hard exclusive processes in GP scattering. This is called central exclusive diffraction. This is the process where the final state of the PP collision consists of the original 2 protons plus a high mass system produced in the middle with rapidity gaps on both sides and with both protons diffracting elastically. It's called central exclusive diffraction. And those processes involve a very interesting interplay of hard and soft interactions. Namely, this high mass system is produced in a hard process that involves the exchange of necessarily 2 partons between the 2 colliding protons. And this, for example, in the case of Higgs production, it's 2 gluons. Otherwise, we would transport color across rapidity intervals, and it would immediately be inelastic. And this hard mechanism has been studied, and people have ascertained that there's some kind of intermediate scale at work that is between the soft scale and this high mass M square. But then, in addition, there is the requirement that the soft interactions of the spectator partons, that they do not produce any particles. Otherwise, again, we would not have a rapidity gap. And this additional requirement of no soft spectator interactions is expressed in terms of a quantity that is called the rapidity gap survival probability, which is defined as the ratio of the full diffractive cross-section to that where we have no soft interactions. So this is a theoretical quantity. It's not observable, but it's the central quantity in the theory of these processes. called the gap survival probability. And again, it can be computed just on grounds of transverse geometry using GPDs and the elastic proton-proton scattering amplitude. And I don't want to go into any details here, but we make a mean field approximation where we suppose that the hard interactions commute with the Hamiltonian of soft interactions because the time scales in the two processes are very different. And this allows us to compute the full amplitude in terms of the gluon GPD and the proton-proton elastic S matrix, and compute this gap survival probability. And it's given in the impact parameter representation in a very intuitive form. It's the integral over proton-proton impact parameters of two factors. One factor, P hard, describes the probability for having the hard double collision at a given impact parameter. This is calculable in terms of the GPDs. The other factor is the probability for having no inelastic soft interactions at this given impact parameter, which is just 1 minus gamma modulus squared. And you can see immediately that these factors have very kind of contradictory dependence on the impact parameter. The probability for having a hard process is largest at small impact parameters and drops very strongly at large impact parameters. On the other hand, the probability for having no inelastic interaction is practically zero at small impact parameters and becomes significant only at large impact parameters. And therefore, the product of these functions is a very curious function that is non-zero only at some intermediate impact parameters. And the integral of that function gives what's called the gap survival probability. So this is really a very interesting case where we have two conflicting requirements. We need to have the protons overlap in order to have a hard collision, but they cannot overlap too strongly because otherwise they would break apart by soft interactions. And the result of that compromise is this gap survival probability. And numerically, we find a value of around 3 or 4%, which is much smaller than what was estimated previously. And we've actually shown that part-1 correlations further reduce this rapidity gap survival probability. And that's I think, very, very important information in the analysis of central exclusive diffraction. And this gap survival probability also has an interesting dependence on the transverse momenta of the diffracting protons in the final state. Again, I will not go into details. This figure shows so the diffraction pattern in the transverse momentum of one proton if we keep the other fixed at a certain transverse momentum, which is now in the x direction here. And you see that we get a very intricate diffraction pattern, and this really attests to the interplay of hard and soft interactions in these processes. And the good news is that this dependence is calculable from the GPDs and the elastic proton-proton scattering amplitude. Very briefly, let me just mention a few more applications and extensions of this. So we can use this logic of transverse geometry to devise a centrality trigger for PP collisions, just by the fact that the hard process with x's around 10 to the minus 1, 10 to the minus 2 selects central PP collisions. Interesting observation is that in such central PP collisions, the small x gluon density in the center of the proton is actually comparable to that, or per gluon density per transverse area is actually comparable to that in a heavy nucleus. So one can reach the black disk regime in helium particle interactions, which is potentially observable in forward particle production. We've also studied quantum fluctuations of the gluon density, which can be defined and quantified in the context of collinear factorization. They're measured in diffractive vector meson production, now not in the elastic diffraction, but in low mass diffractive breakup of the nucleon. And they influence both multiparticle interactions and the rapidity gap survival probability in proton-proton. And one can also speculate about possible measurements of particle-particle correlations in electron-proton scattering. And particularly we've proposed these non-perturbative correlations between C quarks due to chiral symmetry breaking, which are possibly observable in hadron correlations between the current and target fragmentations of DIS with some intermediate kinematics. But so that is summarized. So we've seen that proton-proton collisions are characterized by an interplay between hard and soft interactions. This leads to correlations between the hard process and the event observables, and it kind of forces us or encourages us to think about proton structure beyond just the one-body particle densities. We've seen that a transverse geometry is an essential aspect of the proton-proton collisions. We can get the transverse distribution of the particles from EP gamma P in the form of the GPDs. We've seen that hard processes select central PP collisions. Geometric correlations explain the underlying event characteristics. We've obtained a baseline estimate of MPI rates from geometry and the mean field approximation. And we obtained a baseline estimate of the gap survival probability in central exclusive diffraction. There are many synergies with the EIC physics program. There are, as you've seen, hopefully conceptual connections. We can get input from EP for the next level analysis of PP collisions in the form of fluctuations and correlations. And we should not forget that the proton-proton collisions at the LHC are really the energy frontier. These are the highest available energies we have. So some of the questions regarding small x dynamics, etc., can certainly be studied in these collisions if we use our knowledge of the transverse geometry. Thank you.
Can you show number 11?
Number 11, yeah.
Just the definition of the multiparticle distribution, which is a double distribution. That one is valid in the mean field approximation of the definition there.
This distribution is just defined at independently of the mean field approximation. This is just a product of operators evaluated in the nucleon state, which can be correlated on mean field. Mean field would say that it becomes a product of two functions centered around one point, and then
those are two one-body operators.
Yes.
There you should have one two-body operator, and if you write one two-body operators as a product of two-body operators, you are neglecting correlations by definition.
I think what you're asking is whether this is just this is a two-body density, and to get the correlated part, one would subtract the product of one-body densities, and that's correct. And I have not written down this term, and this is part of this whole issue of how these operators renormalize, how they mix with one-body operators, etc.
Just to make sure.
Yeah.
And
you could write connected part here. So.
Okay, I understand. Another point, you agree that a clear relation with GPDs physics and this multiparticle process is valid only in the mean field approximation. A clear relation.
I would say the connection goes two ways. So yes, in the mean field approximation, you can calculate the multipartal rate just on grounds of the GPD, which is your one body density. At the conceptual level, in sense of a hierarchy of objects, of correlation functions, then there's another connection. So the GPD is the one body density. Here we have two body densities.
Okay.
So
I have questions. It's a connection between EP and a PP you mentioned. When you do the EP elastic process, then
EP elastic.
do the EP exclusive process, then you, in principle, that you can have infinite number of gluon exchange between the diffracted proton and the hot process. That when we say it's dominated by two gluon exchange and a collinear gluon, the defined GPD, because both the gluon participate in the hot process, so they, if we pull the additional one, we pay price of the hot scale, power supply. However, when you do the direct process we demonstrate in the PT process, you do have a one-lot process to gluon coming from two hadron to produce a Higgs, for example. But you have no control the second gluon you to make it color neutral. In principle, you can have any number of gluon there.
Absolutely. Yeah.
So in that case, you may not have the same
Jamie, you're absolutely right, and I just want to say that our calculation of the gap survival probability again relies only on the fact that this process is approximately local on the scale of the variation of the gluon distribution in the proton and transverse space. So we're not hooked to a particular calculation by Jose and collaborators about how this intermediate scale is. This is very tricky. It's really a subject in itself. All we need is that this is effectively local on the scale of soft interactions, and we need to know approximately the scale at which the GPD is evaluated, from which these unintegrated GPDs are generated by evolution. That's all we assume. So you're absolutely right. I mean, the theory of this process, even at the purely perturbative level, is very challenging.
I have a question and a comment. So is anything known from phenomenology about this gaps environment? I mean, Higgs has not been measured yet, but LHC has seen other final states in the center of the
It's a good question. I have to admit that because this is not the main subject I'm working on, I have not followed the latest result. I know there were Fermilab results on diffraction in proton antiproton, which is basically the same at those energies for a central exclusive and also I think single for proton breakup. They extracted something like a rapid gap survival probability, which is a bit larger actually, but again that's in line with our estimates. I don't know the latest status with central exclusive diffraction at the LHC, and
my comment is actually for whatever it's worth, is about the master formula for the cross section. On one of the first slides where you use this, it's actually in a sense to do exactly the same what Matthias Burkhardt does in his picture for the Simmons effect. So he uses the impact parameter dependent GPD, in that case for quark and polarized.
Yeah.
And then he applies it in an inclusive or semi-inclusive process. Yeah. And makes a prediction for the Simmons effect. And here's basically the same.
Yeah, you're saying we should invent some nice name for it, like lensing or
I mean, the picture which we have for the Simmons effect is an approximation. And the same, I think, applies here. I'm not saying that it's not worse.
I need to think about it.
No, this is the lensing is a specific feature which only comes in the Simmons effect. But the very first step of what is done in that picture is you take an input parameter dependent distribution, which you get from the exclusive process, and then you make the statement that this very same quantity should show up in a description of an inclusive process. So this philosophy is the same thing.
Yes, and
I'm just stating it.
And I should say the logic by which an impact parameter dependent picture arrives is actually not trivial. It has to do with what John Way calls absence of interference, and you really say it's not trivial to show that an amplitude or cross section is obtained that is actually diagonal in the impact parameter representation, because it requires using closure, and it depends on the effective momenta of the produced particles. So, for example, the extreme form of that you see in here. If you say that this is a hard process, we know that this has to be local on the scale of the hadronic size in this picture, because the amplitudes could not interfere if these hard production happened in different points. For soft production, this is already not so obvious. You could have interference between amplitudes where the soft production happens with some transverse displacement in the in and out state, and that's exactly what we're seeing in the TMDs. So it's actually it's not a trivial statement.
Not at all.
But I think the core of this idea is that this is what we use always. The total cross-sectional displacement relation. Factorize an interaction from soft interaction because they are on different time scales. That's a basic idea. And then of course one has to ensure that there are no, if they're really factorized, there will be no interference, and then we can calculate the probability of reaction as the product of probabilities.
Mm-hmm.
And whether we can do it actually depends on the quantity. Sometimes we can do it, and the process that we call factorizable or infrared safe are exactly the processes which are satisfy that. And then, of course, in principle, so for what we normally like is if the soft interaction at large time just completely cancel using unitarity or something like that. But in principle, of course, one can imagine a situation that they don't cancel, but they factorize in some other quantity which we can calculate from something else. That's what we do measure this. That will be okay. But the problem is that if we see that the observed is not infrared safe, it just means that this interference can be neglected.
Mm-hmm.
That I would say would mean not. I don't know if it were not infrared safe. That's the main problem, I think.
No, I mean, here this is just regulated by
so this for Higgs, excluding Higgs production. If it would be an infrared safe of overall, then the definition of this SS would be well defined.
Absolutely.
And if it's not infrared safe, then it means that there is a top. There is a cross top.
I think to gain more insight in that, what we should do is really study TMD factorization in impact parameter space and gain more of a space-time intuition for the process in that in that context, because it really means that you have amplitudes where they are forced, say, the hard process happens at a certain space, at a defined space-time point, but then the soft emission can happen at different transverse positions in in the in and out state, and it's this the B that is conjugate to the QT variable.
So, but would it be wrong to say that in principle you have here like Wigner functions and you choose to integrate all PT?
I mean, if you have an exclusive final state, yes. I mean, you could work with it. So
Yeah,
but,
possibly yes. Yeah.
yeah, but this formula, my understanding is it's supposed to apply to any state at this level.
Mm-hmm.
Of which he does not observe PT, but he could choose together.
When you have to have a scale you observe sufficiently long, comparable to the scale you extract.
So there is still B dependence. B is not observed, so it has to be recontribute to something that you observe. Eventually, it might be the PT of the produced jets or whatever.
Our B is a hidden variable here. It's if you like this.
Actually, it's a common. I noticed that you keep emphasize hot process. It's very important because the famous result. People use a defect PDF extract from a Herald apply to the defect event at the formula.
Yeah, this is exactly. Absolutely. This is exactly the gap survival probability.
Yeah, that one is if you apply that, you're in trouble.
Yeah, and actually, we contend that central exclusive diffraction, where the protons don't break up, is a simpler case theoretically because we can use the GPDs rather than the diffractive PDF to calculate the gap survival probability. We have no theory at the moment how to extend this to diffractive dissociation on the proton side. All right. So, okay. All right. Thank you all for your patience.